All right, welcome back to another edition of At-Home Chemistry Labs, live from my basement here. I'm going to go ahead and walk you through the percent of copper in brass alloy lab. So in the intro activity, we're going to be taking a look at 6 solutions. The first 2 are copper solutions. The second 2 are iron 3 solutions. And the last 2 are zinc solutions. One of the goals of the intro activity is to figure out what in these solutions is actually causing these solutions to be colored. You probably remember from first year chemistry that it is the metal. From the background information of the lab, they told you that it's because of the d orbitals, and anytime that transition metals are surrounded by water or other ions, these could be solids as well before they're dissolved. Anytime they're surrounded, that causes the d orbitals to be slightly different in energy. Some are a little bit higher in energy, some are a little bit lower in energy. So when that happens, that d orbital energy splitting, that's called crystal field theory, that matches perfectly with visible light. So what happens is these copper solutions, you'll see, are going to absorb orange light because that is opposite of the blue solution. The iron solutions should absorb kind of violet light, maybe a little bit on the blue side as well, because they're yellowish orange solutions. And we'll see that zinc probably is not going to absorb any colors because it is a clear solution. So let's go ahead and take a look at Logger Pro here. One of the first steps that we need to do is get it calibrated. So I'm going to go up to Experiment and Calibrate. An important step is always to warm up the instrument. In this case, I've already pre-warmed it up, so you would not want to skip the warm-up, but I've already warmed it up, so I can go ahead and skip that and save you 90 seconds. Inside the cuvette here, I have just plain old distilled water, so that is going to help us calibrate our solution. It's always important to wipe off any fingerprints. I'm going to do that right now. We always want to line it up so that the light travels through the clear solutions. So here's the clear side, and here would be the rough side. Hopefully you can kind of see that from an angle. There's a rough side and then a clear side. So we want the clear side to allow the light to go through. So I'm going to go ahead and finish the calibration. And this is simply going to basically allow a clear cuvette and clear distilled water to show an absorbance of 0. Alright, so we are good to go now. Alright, the very first solution I'm going to do is copper 2 nitrate. So again, I've already got the cuvette all set for that. I'm just going to tap the cuvette to get rid of any little air bubbles. I'm going to wipe off any fingerprints. I'll go ahead and put this in here. Notice in Logger Pro, we're doing an absorption spectra. So it's literally going to measure the transmittance of light and then convert that to absorbance for each one of these wavelengths along the bottom here, from like 400 to about 750, maybe 720, 40, 60, 780. Yeah, this is a SpectraViz Plus, so it goes a little bit higher than the regular SpectraViz. So now I'm going to hit Start, and it should give us a nice absorption spectrum. Later what I'll do is I'll blow these graphs up nice and big, one per page, so if you want to zoom in at all on anything that you're having a hard time seeing from the video here, that should help you with that. Now, because I have so many video cameras rolling, I'm videotaping this. It seems like it's a little bit on the slow side. There's a little bit of a lag. Normally, this happens within 3 seconds, and we get our absorption spectra. I'm hoping Logger Pro. Yeah, it's kind of spinning a little bit. Oh, there we go. So yeah, I think just because so many things are running right now, it might be a little bit slower. So this is our absorption spectra. No surprise here, because it's a blue solution, it's going to strongly absorb in the orange region and the red region. One thing that we'll do, I'll go ahead and stop collecting data. And now we're going to get the statistics menu. The nice thing about the statistics menu is that it will calculate what the maximum absorbance is. Looks like I got a little excited with my mouse click there, so I'm going to delete that. Obviously, we only need to do this one time. Okay, so it is showing a maximum absorbance of 1.306, and you can see that kind of makes sense. The top of this peak right here is right around 1.3, so that makes sense, and that happens to occur at 796.2, so pretty much right at 800 nanometers. Now, from the pre-lab, we were reading about how percent transmittance, which is related to absorbance, the instrument can only handle so much light, so there has to be enough light, and there has to be not too much light, or else it'll overwhelm the sample. And the perfect absorbance would be between 1 and 0.1. So if we were going to run the next part of our experiment at this maximum wavelength, or it's called lambda max, because wavelength is lambda, 796.2 would not be a good wavelength for that. That's absorbing too much light, so therefore it's transmitting too much light. Or sorry, it's not transmitting enough light. That light is going to be too dim for this experiment to work out well and give us a nice Beer's law calibration curve. So what we'd want to do is we would probably want to pick a wavelength right around here, something right around 720, 740, yeah, about 740 nanometers. Now, the only problem with that is that when we go on to the next part of the experiment, these solutions all right here are 0.1 molar, whereas in the next part of the lab, our stock solutions are 0.4 molar. So because 0.4 molar is 4 times as concentration, 0.4 is 4 times as concentrated as 0.1 molar, you would get an absorbance 4 times the amount. So if a 0.1 molar solution absorbs at 1, then the 0.4 would probably absorb around 4, and that's definitely going to be not enough light. The percent transmittance would be too low to give us a nice calibration curve. So what we're going to want to do is kind of work backwards and figure out what a good wavelength would be. I'm going to turn on my examine button. Hopefully that works well with this lag. So if we want the 0.4 molar to absorb at 1, we're going to want the 0.1 molar, which is this solution right here, to probably absorb around 0.25. So I'm just going to have to kind of estimate. It doesn't look like my... oh, there it's working. It was just took a little bit longer. I'm going to want this to absorb at around 0.25. So I would say this right here. It's a little too high. If I don't move my mouse, somewhere right around here, because if the 0.1 now absorbs at 0.25, when I multiply that by 4, the 0.4 should still be within range and absorb at around 1. So I would say a good wavelength for this solution in the next part of the lab would be around 639.4 nanometers. Again, that might be different if you're running your own samples, but again, because we're going to want to quadruple the solution concentration for the next part of the lab, we're going to want this to start out with an absorbance of about 0.25. All right, what I'm going to do is I'm going to go ahead and save this. We're going to move on to the next solution. We'll store the latest run. Alright, so for the next sample, I'm going to wipe off the fingerprints. You can see it is copper 2 sulfate. So this solution will look pretty similar to first year chemistry. You probably did an unknown hydrate lab, and that was copper 2 sulfate pentahydrate. You made calibration solutions and standard solutions of this copper 2 sulfate, very similar to what we're going to be doing in the guided inquiry portion of this lab, except we're going to be using the copper 2 nitrate. So it's a blue solution. I'm going to put it in here. That should give us a very similar absorption spectra as the first one, because again, it is the copper, not the nitrate, not the sulfate, but it is the copper plus 2 ion that is giving us this color, so therefore the absorption spectra should be very similar. So I'm going to go ahead and press stop. I'm going to be patient and wait for that. And now, when I do the statistics, let me get rid of the first statistics. When I run the statistics on the second solution here, the copper 2 sulfate, this would be the latest one. You can see, again, we get very similar results. It has an absorbance, a max absorbance of 1.331 at 799.3 nanometers. Yeah, 799.3 nanometers. Again, that's going to be too high. So if we were just studying 0.1 molar solutions, we'd want to probably back that off to right around here, because this would now have an absorbance of 1. So that would occur at around 736 nanometers, because in the next part of the lab, though, we're going to move up to a 0.4 molar solution. We're going to want this to absorb probably closer to the 0.25 range. That's still a little too high. Yeah, so right around here. So again, right around 630, around 640 nanometers. This is coming out pretty close to 640. Alright, so we are now done with the copper solutions. I'm going to save that again so I can go back to it later and blow up that solution nice and big so that you guys can see that and zoom in on those numbers. We want to store the latest run. Alright, now I am moving on to the iron 3 nitrate solution. So iron 3 nitrate. Go ahead and wipe off any fingerprints. And it looks like it is done measuring, so I'm going to press stop. You can see this solution looks a lot different because it's kind of an orange solution. It should be absorbing in kind of the blue-green region. There we go. Probably even more so the violet region. I guess it depends on how yellow or orange the solution is. I would say this is in between yellow and orange. So yeah, it should absorb pretty strongly in the blue or violet region. And sure enough, it is. So what I'm going to do is add the statistics for this. The latest run. Okay, so according to this iron 3 nitrate solution, it looks like it has a maximum absorbance of 1.38 at around 400.2 nanometers. So again, if we were going to move on to like a beer Beer law, calibration curve, an absorbance of 1.348 is absorbing too much, therefore it's not going to transmit enough light. So let me just get my little examine feature going here. So if we were only studying 0.1 molar solutions, just like this is, you could probably get away with a wavelength maybe around 418, 420, because that has an absorbance pretty close to 1. Whereas if we go down here, if we bump it up to a 0.4 molar solution, like we're going to do in the guided inquiry lab, we're going to want to be closer to like 0.25. Yeah, so somewhere right around here. So for this solution, a wavelength of 503 nanometers would be better. Again, if we were going to quadruple the solution concentration and get around 0.4 molar. All right, let me go ahead and save this. I'm just going to go up here to notifications and turn off any notifications, just so we are not bombarded with those. Okay, so we're back. All right, so the new sample that we're looking at is this orange one. If I take it out, it's going to extremely drop. Yep. So yeah, we are looking at the orange line right now, which is for iron 3 chloride solution. So it should be pretty similar to the iron 3 nitrate solution. I thought this one was a little bit more on the yellow side rather than the orange side. So we might get a slightly different absorption spectra. I would think yellow would more strongly absorb in the violet region than the blue region. So if we take a look right here, I can go ahead and press stop, and then we can get our statistics for this solution. All right, so we're going to do the latest run. All right, so this one is showing a max absorbance of 1.5 at around 400.2 nanometers, just like we would expect right here. So again, the maximum peak is tapping out right at about 1.5 here, and that's right around the limit of our instrument, which is about 400 nanometers. So again, if we were going to do an experiment just on 0.1 molar solutions, we would want to keep that absorbance under 1. So we can see here, if I'm just estimating, that's going to probably be around 440. Maybe closer to 430. So yeah, this is showing around 428.1 nanometers. Has an absorbance of 1.011. So that's probably good enough. Now, if we were going to scale this up like in the guided inquiry portion of the lab to a 0.4 molar solution, we would want to cut this absorbance down to about 0.25. So we can see what that is right around here. Actually, that was pretty good. So we'd probably want to go with a wavelength closer to 468.1. 468.1. All right, that wraps up our iron solutions. So let's move on to our clear zinc solutions. The next one I'm going to do is zinc nitrate. And this is a clear solution. The reason for that is zinc its electron configuration would be 4s2 3d10, and this zinc right here is a +2 zinc, so it's going to lose those s electrons. So it still has 10 d electrons. So even if those d orbitals split a little bit when it's surrounded by water molecules and ions in solution, it won't be able to allow those electrons to absorb visible light and hop back and forth because all of those d orbitals are filled. There's no room for those electrons to hop back and forth. So this should not absorb visible light. Let's store the latest run. So you can see that bottom line is hardly even visible. I guess it's a purple line just because it's basically not absorbing any visible light. So I'm going to go ahead and stop. And we'll pull up the statistics for this. But again, we shouldn't see a maximum absorbance very high. It's going to be very low. We'll run the statistics button for it. Yeah, and it has a maximum absorbance of like 0.009, so pretty much nothing. So again, that is supporting the fact that this is a clear solution. So using a visible spectrophotometer would not be a good instrument to study zinc solutions. Now, it would be cool, I don't have it here, but at school we have a UV vis spectrophotometer. There's a chance that maybe this zinc solution would absorb ultraviolet light, and then if we got a peak in the ultraviolet region, then we could study zinc solutions using that ultraviolet light. But yeah, a visible light spectrophotometer is not going to be a good instrument to study these zinc solutions. Just so that we have all the solutions. Again, we should get similar results for zinc sulfate. Because again, it's a zinc +2 ion. It's got a D10, a 3D10 configuration. So we'll put it in here. We'll save and continue. Get rid of my statistics. So it looks like this new colored graph will be kind of maroon. And again, it's so low you can't really see anything down there. So we will run the statistics button on it just to prove that. I guess it didn't register me pressing stop. So let's press stop. It's going to have a hard time measuring statistics on a moving target. So that's why you always have to press stop. Once you press stop, then it can calculate those statistics. And we should pretty much get an absorbance of 0. So at its maximum absorbance, which is right around here, around 800 nanometers, 799.3, it's absorbing 0.002. So yeah, that pretty much is not absorbing visible light. So I hope that helps you answer or collect your data for the intro activity. Hopefully these results help you to build your procedure and answer the guided inquiry questions. In the next video, I'll be showing you the calibration curve using the standard solutions of copper 2 nitrate. We're going to build a calibration curve so that in part B, or part 2 of the guided inquiry lab, then we can dissolve that brass sample and measure what the concentration of the copper is in that brass sample. All right, have a great day. All right, welcome back to part 2 of the lab, the guided inquiry portion. If you remember, Back to the intro activity, we took a look at a bunch of metal solutions, transition metal solutions. They all have d orbitals. Most of them were colored, whereas the zinc solution was not. So copper 2 nitrate looked like this. Copper 2 sulfate looked like this. Iron 3 nitrate had an absorption spectra that peaked in the violet because it was kind of a yellow solution. Iron 3 chloride also peaked in the violet region because it was a yellowish orange solution. And then the zinc nitrate did not have a peak because it was a clear solution. The zinc sulfate also was clear, so it basically had no absorption. And now today we're going to be working on the calibration curve. So let's go back to that copper nitrate solution. This is the graph that we're really going to focus on. And the reason for that is that we're going to take our brass and dissolve it in nitric acid, concentrated nitric acid. So therefore we're going to be forming copper 2 nitrate. So just remember, our spectrophotometers work best when we have an absorbance between 0.1 and 1. That lets like the sweet spot, just the right amount of light through into the instrument. So you can see here, if we went with the maximum absorbance or the lambda max, that would be at 796.2, and that is over the absorbance of 1. Plus this was a 0.1 solution, whereas we're going to be using a 0.4 molar solution as our stock solution, so that would be 4 times the absorbance as this. So we estimated in the intro activity that we were probably going to need to go with an absorbance close to 0.2. Let me get my inspector out here. I'll move that so you can see. So we kept going up until we had an absorbance close to 0.25, right around there. And we're thinking that this is probably going to be good at 639.4 nanometers. Now we'll actually figure that out when we put in the 0.4 molar solution, and we're going to do that in a little bit here. But we're going to go ahead and make our standard solutions. So let me go ahead and get back to the calibration curve. So before we make the solution, we're going to need to, before we make the graph, we're going to need to make our standard solution. So let's just go ahead and get the spectrophotometer all set up here. I've already warmed up the lamp, so we can go ahead and skip that. Again, you would not want to skip that warm-up phase, but this instrument has already been on, all set to go here. So I'm going to go ahead and skip the warm-up. Right now I just have distilled water in the cuvette. Again, clear sides go through. I've wiped off all the fingerprints. I'm going to finish the calibration. Okay. Now, if I put the 0.4 molar stock solution in, we can see how close to that actual absorbance peak we're going to get. So we'll go with start. We're just going to erase and continue. And it probably is not showing anything here just because it's off the scale. Let's just make sure it's showing the latest absorbance. Yep. And let's go ahead and auto scale it. All right, so I'll do it one more time, and you can see what we're talking about, that if we go at the maximum absorbance peak, it's kind of jumping all over the place here. And that's why we can't use this peak here, because it's up in the 2s and 3s. It's absorbing so much light that it's letting very little transmit through, and we're not going to get good results here. So again, we want to keep this absorbance as close to 1 as possible. So that would be this right here. Pretty close. Yeah, and we sure enough get about 638.6. So that's going to be the wavelength that we go with for this part of the experiment. But right now we have to make the standard solution. So let's go ahead and do that right now. I already have the stock solution, which is our 0.4. In the lab, you had two options. I think your procedure called for making 8 milliliters of solution, just because that would probably be enough. But you can see here I have a 10 milliliter volumetric flask. So we're going to make our solutions in that. So I scaled everything up to 10 milliliters. You could do 8 milliliters in a graduated cylinder, but a volumetric flask is going to give you much better results. And I think I changed that in the procedure for next year. I'm not sure if you got the updated version or not. So we're going to go with a 10 milliliter solution. So we could make this multiple ways. If we wanted to make the 0.2 molar solution, in the intro activity or in the guided inquiry, you calculated how much of the stock solution we would need. Well, if we're going to make a 0.2 molar solution, we would need half the new solution to be the 0.4 molar, and we would need about half of it to be distilled water. So I'm going to go ahead and do that right now. So I have a micro pipette right here. It is all set for 1,000 microliters, which would be 1 milliliter. So I'm going to inject 5 milliliters of my stock solution and then water it down up to the 10 milliliter line. Now I'm not going to add 5 milliliters of water because when making solutions, the volumes are not additive. So 5 milliliters of the stock solution, 5 milliliters of the distilled water might not actually be exactly 10 milliliters, but we just care that the total volume is 10 milliliters. So we'll just add distilled water the rest of the way up until we have our 10 milliliters of total solution. So I'm going to press this down to the first plunger position. I could go all the way down, and that's how we're going to eject the sample. But to fill it up, you go to the first position. We'll put in our micropipette. We'll suck it up. So this would be 1 milliliter all the way down. Go for a second. All the way down. Go for a third. Eject all of it. Go for a fourth. Eject. And go for a fifth. All the way down. Alright, so I'm going to try to get rid of that little speaker button. Yep, there we go. I just have to be off the screen. Okay, so now I have my 5 milliliters of stock solution. So now I just need to water it down the rest of the way. I want to get it exactly on that meniscus line. I'll hold it up there. The bottom of that meniscus needs to be directly on that white line there. Get it as close to that line as possible. Just need like one more drop. Perfect. Now, as far as this solution goes, we could add this directly to the cuvette, and now this would be half of the 0.4 molar strength, so that would be 0.2 molar. You do want to be careful. I'm just going to put some distilled water in here so I can rinse out my pipette. So I'm just going to transfer that solution to my cuvette. Now you do want to be careful because this is such a small volumetric flask. There's a chance that maybe not all of this solution is homogeneous. We probably have a little bit more distilled water at the top, a little bit more solution at the bottom. So I'm going to try to mix that up a little bit. So I'm going to suck some sample up. I'm going to squirt it in from the bottom, suck it in from the top, squirt. Go like that. So I think after mixing that up a little bit, that should be a fairly homogeneous solution. So now I just need enough of this sample in my cuvette for the calibration curve. So I have my paper labeled here. This is my 0.2 molar strength. Just going to put that in the cuvette. And again, it should be about 2/3 to 3/4 of the way filled. You don't want it too low. Or else that solution won't have the light shining through it. So you can see this is a much lighter solution than the original one. Darker blue for the 0.4 molar, lighter blue for the 0.2 molar. Now we have several options for the next solution. The next solution we're going to try to make is the 0.1 molar. That's what we used in the beginning of the lab. So I could go right back to my stock solution and I could calculate how much of this I would need to get to 0.1 molar. It would only have to be a quarter of the 10 milliliter total solution. So we're talking like 2.5 milliliters. So I could take 2.5 milliliters of this, add it to the volumetric flask and distill it. Add distilled water the rest of the way up to the 10 milliliter line. And I think most people did their guided inquiry procedures like that. I just want to show you what a serial dilution looks like, especially for really dilute solutions. It's oftentimes best to take the solution you just made, the 0.2 molar, and dilute that further. So if I want to take the 0.2 molar now and dilute it down to 0.1 molar, I would need half of that solution. So what I'm going to do, I'm just going to clean out this beaker a little bit with some distilled water. Ideally, we'd be using clean beakers every time. We dry them out so that any distilled water in this beaker would not slightly dilute our results, but I'm going to try to get rid of most of it as possible. So now we're going to have to get our solution out of here. We would need 5 milliliters of this. We're going to use the same micro pipette as before, but it's going to be really hard to pipette out of this volumetric flask. So what I'm going to do is just pour that solution into my beaker here, so it's a lot easier to get it out. So I do see some water in the bottom here. I'm going to try to suck all of that out so it doesn't interfere with our results. Alright, so now I have my 0.2 molar solution in the bottom of this beaker, and we're going to have to suck up 5 milliliters of this and put it into here. Now because this is 0.2 molar residual in here, I'm going to rinse this out with some distilled water just so we don't end up contaminating our results. Again, ideally if we were in a lab setting we would clean all of these out each and every time. There is a little distilled water left in here, but because we're going to be diluting the rest of the way with distilled water anyways, that shouldn't affect our results. So again, we could have taken 2.5 milliliters of the stock solution, watered it down to 10 milliliters with distilled water, but I'm going to take my previous solution, the 0.2 molar, and suck up 5 milliliters of that and dilute that the rest of the way, because that'll cut it in half. So again, I'm going to grab 5 milliliters of this. There's one. Two. Three. Four. And 5. Now what I need to do is dilute this the rest of the way with distilled water. So again, it'll be about 5 milliliters of distilled water. But again, I'm not measuring that out because we just want the total solution to be exactly at 10 milliliters. I'm going to get that meniscus exactly on that line. Perfect. And again, because the top of this sample might be a little bit more dilute, more distilled water, I'm going to suck some sample up. And just kind of keep squirting that back and forth in here to fully mix up this sample. Grab some sample from the bottom, bring it to the top, and fully mix this up. Again, normally we would transfer this volumetric flask solution into a container, into our test tube, so that would give it a chance to mix. But I'm just going to kind of mix it up this way. So now that that is homogeneous, I'm going to pull my sample. And I have a cuvette here labeled as 0.1 molar because it's half of the 0.2 molar concentration. I want to fill it most of the way to the top. And now we just have one more solution to go. So the last solution we're going to make is the 0.05 molar. And again, if we started with the stock solution and we're making 10 milliliters of sample, you would only have to take 1.25 milliliters of this, water it down to the 10 milliliter mark, and then you would have 10 milliliters of total solution, which is that 0.05 molar solution. The problem is the smaller and smaller and smaller concentration you get, the more dilute it is, you might have a hard time measuring that really small quantity. Now I could do that here. I could do 1,000 microliters and then 250 microliters, but because we got a good system going here, we have a serial dilution going. I'm just going to take the rest of that 0.1 molar solution, dump it into my clean cup here, so that it's easy to pipette it out. And now if I water this down by half, that would take me down to the 0.05 molar solution. So I'm going to suck up 5 milliliters of this and put it into my 10 milliliter volumetric flask. So I'm going to rinse that out with distilled water one more time, just because right now there is probably a little bit of leftover of that 0.1 molar solution in there. And we don't want that to skew the results. Again, if there's a little distilled water left in there, not a big deal, just because we're going to be adding more distilled water anyways. All right, so I'm going to suck up 5 milliliters. So there's 1. Here's 2. 3. 4. And 5. So then the last step would be just to finish diluting this the rest of the way with my distilled water. And again, I'm going to do that up to the line. Try to stir and mix as we go. Need a little bit more. One more drop. Perfect. So now I'm just again going to mix up this solution. Make sure it's evenly mixed from the bottom there. And now I have to just pull up this solution and put that into my cuvette. And now the rest of that we should be able to dispose of. So as far as the Beer-Lambert law goes, I'm going to try to get a good picture of this. This is our 0.4 molar solution. This is our 0.2 molar solution. This is our 0.1 molar solution, our 0.05 molar solution, and our good old distilled water. So you can see this definitely kind of creates a nice linear fashion here. The most dilute, the distilled water, all the way up to our highest concentration, the 0.4 molar. Now all we have to do is actually quantitatively measure that. So we're going to go ahead and set up our spectrophotometer. Here we did a full absorbance spectra, whereas now we just want to pick the one wavelength, which should be that 638 nanometers. Again, we want our full highest concentration to have an absorbance of about 1. So I'm going to go to data collection. I'm going to switch the mode to events with entry. I'm going to say calibration curve. And now we have to pick the correct wavelength. Oops, I think I forgot. Yeah, it's not this button we need to pick, it's this one right here. So we want to configure the spectrophotometer. So right now we're doing absorbance versus concentration. Let me switch that back. So full spectrum. Okay, yeah, so I'm going to click the rainbow button. Absorbance versus concentration. This is trying to pick the maximum wavelength, which was really close to 800 nanometers, but we know we need a wavelength closer to 1, an absorbance of 1. So sure enough, it picked the 638 point, can't quite read that, 638.6 nanometers. So that is where we are going to measure all of our samples at. So I'm going to click OK. So you notice the rainbow disappeared because, again, we're not measuring every single wavelength right now. We're only measuring at that 638.6. So I'm going to start collecting data. All right, so once this stabilizes, we can see that sure enough this has an absorbance pretty close to 1. I'm going to go ahead and insert a meter just so we can see that a little bit better. I should be saying absorbance. There we go. That's what I wanted. So yeah, we want this to be absorbance at 638.6. Insert a meter, digital meter. Normally it says it right down here. We want that to say latest absorbance. There we go. So because we set this up properly, because we picked the correct wavelength, 638.6, sure enough, this is absorbing pretty close to 1. So now I'm going to keep that value. I have to write down and enter what the concentration is. So this was the 0.4 molar. So I'm going to hit enter, and it just adds a little data table here. And this is the information you want to put into your lab notebook, that the 0.4 molar standard solution or the stock solution had an absorbance pretty close to 1. It was 0.996. So now I'm going to take that one out. We're going to go to our next sample. I'm going to wipe off the fingerprints here. This was our 0.2 molar. It should be half the concentration, so about half the absorbance. We have to wait for this number to kind of stabilize down here. Sometimes people click the keep button a little too fast. So we're going to let that stabilize, and sure enough, it's about half, or 0.5. So I'm going to keep. This concentration is 0.2. Okay, it added another data point for us. Take that out. We're going to do the next one, which is the 0.1 molar. Wipe off my fingerprints here. Let it stabilize. This should be about quarter strength or quarter absorbance. Pretty close, 0.25. So we'll keep. This is the 0.1 molar solution. 2 to go. This would be our 0.05 molar solution. And that has stabilized. Yeah, that should be at about 1/8 of the original strength, so about 0.125. Sure enough, it is. Keep. This is 0.05. And finally, we should probably put our distilled water in there. That should have an absorbance of 0. Sure enough, it does. This is our 0 strength. So what you can see is up here we have a really nice, beautiful calibration curve. It looks very linear. So once I hit stop, then we can do the linear statistics for this. So we'll just hit the line of best fit. And that's enough to almost bring one to tears. So we have our slope that you want to write down. So absorbance is equal to 2.501 times the concentration, because that's our x-axis, plus a negative 0.006513. So it has a y-intercept of a negative 0.00653, which that should make sense. That's pretty much the number 0. When the concentration is 0, the absorbance should pretty much be 0 based on our distilled water. And what is beautiful is this correlation constant, or correlation factor. It's 0.9999. It doesn't get much better than that. If you square that, you'd get the R squared value. But really what we want is the correlation between absorbance and concentration, and this is pretty much a perfect Beer-Lambert law correlation. Now what we'll do in the next video, once we have our blue sample from the brass that has been dissolved in nitric acid, we will put the solution in here and see how blue it is. Let's just say it ends up being, I don't know, about 0.7. We can go down here using the equation and we can figure out what the concentration of the copper is from that brass sample. So stay tuned for video number 3. Alright, welcome back to our third video on this lab where we're calculating the percent of copper in brass. So I've got my 2 decimal place balance set up here in the basement. We've got our brass sample, our little weighing dishes. Ideally we would be doing this on the analytical balances so that we had at least 3 decimal places, if not 4, but we got to go with what we've got here. So this balance has been warmed up. I'm going to put the weighing dish onto the balance. Obviously we want to 0 that. And now it says in the guided inquiry part B of the lab that we need like 2 pellets of brass. So I'm just going to pour out a couple here. So this is the size pellet we're talking about. So they want us to get about 1 gram. So I'm just going to get 2 of those pieces. And sure enough, that weighs about 1 gram. So 0.97 grams. Looks like it's pretty stable. So you're going to want to write that down in your lab notebook. So we have 0.97 grams of brass. And when we're done with this lab, we should calculate the mass of the copper from how blue the solution turns once we add the nitric acid. So then once we know the mass of the copper, we know the mass of the brass is 0.97. We can turn that into a percent by mass. So I'm going to pause the video right now and go outside after writing that number down, 0.97 grams, and I have to do the nitric acid outside just because that'll produce nitrogen dioxide gas, which is that brown fuming gas, and yeah, that would not be good to do in the basement here. So I'll be right back. Alright, so we're back to part B of the guided inquiry lab. We're going to be dissolving the the brass in the nitric acid. So we're definitely doing this outside so that we don't inhale the nitrogen dioxide fumes. The brown bottle contains the concentrated nitric acid. I believe that's 15.8 molar. Take a look at my calculations here. Yeah, 15.8 molar. I've got the graduated cylinder to measure that out. We've got the brass. I've got my lovely lab assistant. Say hi, Evelyn.
Hi.
All right, so I just wanted to walk through the math real quick. We have 0.97 grams of brass. So the question is, why are we adding 6 milliliters of concentrated nitric acid? So I just wanted to walk you through that real quick. If you take a look at the top equation, this is our balanced chemical equation. Copper plus 4 nitric acids is going to react and produce copper 2 nitrate plus 2 nitrogen dioxide molecules and 2 waters. Now, if we split apart the nitric acid, because it's a strong acid, we'd get copper is reacting with 4 hydrogen ions or protons plus 4 nitrate ions. But then on the right-hand side, we also have 2 nitrate ions. So 2 of these nitrates here are going to cancel out these 2 nitrates here. So that's why we only have 2 nitrates on the left. You're going to get the copper plus 2 ion, which that's the blue chemical we're going to be measuring. 2 of these nitrates here turn into 2 nitrogen dioxide gas molecules. That's that reddish orange brown gas we'll see, plus some water. So I had you do pre-lab question 5. And if we had 1.5 grams of copper, how much nitric acid would we need? So this is just a stoichiometry problem. You take the mass of the copper divided by its molar mass, 63.55. According to the balanced chemical equation, it's a 4-to-1 ratio. So there's 4 nitric acids for every copper. So 4-to-1, there's 1,000 milliliters, or 1 liter is 15.8 moles per liter. So that gives us 5.98 milliliters. So that's the maximum amount that we would need, or the minimum amount we would need for 1.5 grams of copper, because we only have 0.97 grams of brass. Assuming this was 100% copper, we would need that much to fully react it. So the fact that we're well under 1.5 grams, I think 6 milliliters of nitric acid should be plenty for this. So I'm going to go ahead and set up the camera so we can watch this. I'm going to move the beaker so it's at a good location so we can see it. I'm going to pour the nitric acid into our graduated cylinder. So I'm going to do this. I've got my lab goggles on. Again, this would be very dangerous. You would not want to get this on your skin. So I'm going to add approximately 6 milliliters.
Where is it?
All right, Evelyn, you're going to add the brass beads to the beaker. Can you go ahead and put them in the bottom of the beaker? Now we'll just sit back and watch. I'm going to try to keep that to one side because, again, 6 milliliters isn't very much acid. And you can see immediately there is a chemical reaction taking place. So I'm going to tip that up on that.
There's green. Wait,
So Evelyn just noted that there is some green forming. Those would be the copper +2 ions. Depending how concentrated it is, it'll be bluish or greenish. You can see the red fuming nitrogen dioxide gas. And again, this is exactly why we want to do this outside. We don't want those fumes to get in the house. So we'll just let it sit here for a little bit and react. And at some point I'll turn off the video and then I'll take you back down to the basement with the final solution. Do you smell that smell? You can kind of smell a musty smell right now, or at least I can. This is one way I know that a car's catalytic converter is not working. When a car sucks in air to burn with the fuel, 80% of the atmosphere, or 78% of the atmosphere, is nitrogen. And when that nitrogen gets hot and hits the catalytic converter, some of the oxygen in the air and the nitrogen in the air is converted to nitrogen dioxide gas. So as I'm walking down the sidewalk, especially when I come up to a car stopped at a stop sign, if I smell kind of a musty odor, it kind of bites your nose a little bit, I can tell that their catalytic converter is not working properly. And in Pennsylvania, that's why you have to get 2 stickers every year. You not only have to get the inspection sticker to make sure that your car isn't completely rusted out, its brakes are in good working order, and the lights are working, but we also have to make sure that we're not putting all these polluting gases into the atmosphere. Alright, so I think that probably gives you a pretty good idea of the reaction that is occurring. You can see that it's pretty potent, that really reddish orange gas, and we've got the bubbling, fuming brass down below here. Eventually those brass beads will be completely dissolved. Alright, so I'm just checking back in on our reaction. You can see we still have some brass down below there. The gas isn't quite as orange up top. A lot of that orange nitrogen dioxide gas has dissipated. I'm just going to blow down into the beaker just to give you some better observations of the solution down below there. It's a little bit easier to see down in that beaker when the gas isn't all present. I can tip it a little bit this way so you can see down in there. But again, this would normally be done in a fume hood, and then the next day you would just come back and find this completely blue, if not green, solution containing copper ions. You'll notice that color is very distinct, kind of similar to the Statue of Liberty. That's one color of verdigris. Verde means green, so when copper oxidizes naturally outside, it forms this chemical compound known as verdigris. It's a kind of a family of compounds, and again, it gets its name from it being a green color. Green minerals, green solutions, or if they're a little bit more dilute, maybe more so on the blue side. Alright, so we're about 10 minutes into the reaction. You can see there's very little nitrogen dioxide left. Most of that is dissipated. There's still a little bit left being produced because there's tiny little pellets. You can see towards the top of the beaker there, tiny little pellets. They just bumped into each other. So there's still a little brass that needs to dissolve, but I have a feeling in the next 15-20 minutes they'll be done reacting. Alright, you can see here for this last part of the lab we have upgraded to kitchen chemistry. So I just again did the dissolving of the brass sample in nitric acid outside on the back porch just because of all the fumes. So now that the kids are in bed, I don't think we'll get interrupted here. Let me go ahead and get the iPad all set up. So now if we take a look down inside the beaker, you can see that all of the brass is gone. It's been completely dissolved. And again, if brass is an alloy of copper and zinc, we now have a solution of zinc ions, copper 2 or copper plus 2 ions, and a whole bunch of nitrate ions. And about half of the nitrate fumed off as nitrogen dioxide. So now what we're supposed to do is dilute this with distilled water, preferably to 100 milliliters. The problem is in my rush to leave school, I didn't grab all the materials that I probably should have. I thought I got everything I needed, but I only grabbed a 50 milliliter volumetric flask. So I think what I'm going to do is I'm going to take this solution, get all of the solution into the volumetric flask, water it up to the 50 milliliter line. We'll test the absorbance of that solution so that we can calculate the copper ion concentration. I have a feeling it'll be too concentrated, so then what I might have to do is dilute that one more time. Because again, if we take this blue solution and dilute it to what we should have, 100 milliliters, that's basically diluting it to 50 and then diluting it to 50 one more time. So it's not exactly as efficient as I was going to hope it would be, but who knows? Maybe we'll get lucky and maybe this solution is still on our calibration curve under that maximum point. So I'm just going to kind of keep my eye on that 50 milliliter line. I'm just going to add some distilled water. This is still fairly concentrated acid, so I'm just going to water it down just to make it a little bit safer to work with. I definitely want to keep that water level well below the 50 milliliter line, because as I pour that into the volumetric flask, there's going to be some residual copper ions or blueness left in the beaker, and obviously we want to make sure that all of that gets rinsed into our volumetric flask so that we don't leave a single copper atom behind. Alright, that is probably good enough. I don't have a funnel, so I think what I'm going to do is I'm just going to suck this liquid up using a pipette. Again, we're not really dealing with that much solution, so I don't think this will take that long. I'm trying to guarantee that I'm getting all of those blue copper +2 ions into the volumetric flask. It's a pretty blue color. There's still some blue residue left in the bottom of the beaker. So I'm just going to rinse that down in. I'll suck up that. Maybe do it one more time, and then we'll finish diluting to the 50 milliliter mark. All right, it looks to me from the beaker that we got all of that blue copper 2 ions out of there. So now I think it's going to be safe to finish diluting this the rest of the way with our distilled water. Just want to make sure there's no blue copper ions up here in the neck. I'm going to kind of mix that as we go. Again, we're going to stop when the solution level is exactly at the 50.00 milliliter line. I'm going to get on eye level here. Try to tap out those air bubbles. Oh, meniscus is a little bit on the low side. A little bit more. One more drop. All right, and that right there looks good to me. Okay, so now I'm just gonna kind of swoosh this around a little bit just to make sure it's evenly mixed. And it's actually probably going to be better if I just pour this out into the beaker. And I'm just gonna quick grab a paper towel and dry that out. Because again, if there is some water in there, we don't want that distilled water to dilute our sample further. So again, there was nothing magical about diluting it to 100 milliliters. It's just I have a feeling we're going to have to do that to get the absorbance within the range. But again, maybe this will work. So I'll finish taking this back down into the basement. We'll fire up the spectrophotometer. We'll get it recalibrated and we'll see what the results are. All right, welcome back. So just to review what we just did, we took our nitric acid and brass sample that has been dissolved. We just watered that down, diluted that to 50 milliliters, and we made a solution. I'm hoping that this level of blueness or the absorbance of this blue solution fits on the calibration curve that you see in the background here. If its absorbance would go over 1, we'll probably have to do one more dilution Again, just because I didn't have that 100 milliliter volumetric flask at home. Normally I keep those in my basement, but I took those to school for an upcoming demo show that got canceled, so we'll just have to make do without it. So I went up to calibrate the experiment. It's been a while since I was using the SpectraViz, so I did warm it up. So I'm going to go ahead and click finish. Right now I just have my distilled water sample in here. Anytime you start a spectrophotometer, you should warm it up and calibrate it. Okay, so now for the moment of truth. Again, we are measuring the absorbance of our blue solution at a specific wavelength. It's been a while since this afternoon. Usually I think it says what the absorbance wavelength is. I thought maybe it was in the 600s, maybe 638 something. I'm not sure why it's not saying that right there. I can probably go into the settings just to double check that. I'm not exactly sure why that's not saying 638 anymore, but we'll hope for the best and see what we get. It is pretty important that this blue solution that we're measuring right now gets measured at the same wavelength. I'm just going to click this to float on top. There we go. Alright, so again, if this isn't under the right settings, I might have to play around with Logger Pro to fix that. So I'm just going to fill up our cuvette with our copper solution. Alright, and so far this is a good sign that this isn't measuring over 1. I'm just going to click up here and... Alright guys, I'm back one more time. I wasn't really happy with how our graph was no longer saying the absorbance, what wavelength that absorbance was measured at. I was pretty sure where we left off the previous video, this said absorbance at 638.6, because again we had to pick the wavelength. So I'm not exactly sure how accurate that interpolation calculator was, because if it was running at a different wavelength, which I think it was possibly running closer to like 600, obviously the absorbance will be different, and when you plug that absorbance into this line of best fit, that's going to give you a much different result. So what I did is I just switched it back to 638.6. So again, I just went up here to the configure spectrophotometer. I switched it back to 638.6, and now we're getting a absorbance at a higher value, which would make sense if it was measuring at 600 before. Lower on that peak, it would get a much smaller absorbance, whereas measuring at 638, again, it's getting closer to that 800 nanometer, which was the max. So I think I'm going to run this interpolation calculator one more time, and I think this is going to give us much better results. So I'm just going to go to Analyze, Interpolation Calculator, and the curve fit would be the linear fit for run 2. And for some reason it's not giving us a value here. I mean, we can type the absorbance of 0.527. Oh, okay. So yeah, normally it just measures that. Let me try one more time. So we've got our linear fit. I'm going to get rid of, I'm going to take a screenshot of this just in case we need it again. I'm going to get rid of this one. And yeah, I'm just going to try doing that linear fit one more time. Okay, yeah, that's what we had before. That's a good sign. So analyze interpolation calculator. Again, it's not showing up there for some reason, but this time it's 0.526. And I don't think we're going to argue about a thousandths. So I'm going to go ahead and write that down. Absorbance equals, and I'll post this graph online so you guys can see it. Absorbance is 0.526. And the concentration is 0.2129. 4 sig figs, 3 sig figs is probably good enough. 2129. Good. So, okay. And I'm going to take a screenshot of that. All right, so now we should have all of the data that we need for the Postlab. All right, so I just wanted to make this little video to go over some of the calculations in case you were having trouble as far as the Postlab goes. So in the last part of the lab, we figured out that the absorbance of our unknown solution was 0.526. And from the line of best fit, that gave us a concentration of 0.2129. And that would be moles of copper 2+ per liter. So now the goal is we want to know how much copper is present. So if we just set up a little conversion, we have 0.2129 moles of Cu per liter. And if you remember that we took our dissolved brass and watered that down to 50 milliliters, and 50 milliliters is 0.05000. So 50 milliliters, move the decimal 3 times because there's 1,000 milliliters in a liter. I'm just going to undo that. So that's how many liters we had. This will give us the answer of moles, so 0.2129 times 0.05 with 4 sig figs. 4 sig figs, we'll keep 4. That gives us 0.0106. And the 4th sig fig will go with 4, and then there's like a little 5. So that 5 doesn't count as being a sig fig, but we'll keep it in our calculator for the next calculation. So that would be moles of copper. Now to turn that into grams, we're going to multiply by the molar mass of copper, which is 63.55 grams of copper per 1 mole of copper. So that really should be our last step. Multiply that previous answer by 63.55, and that gives us, with 4 sig figs, 0.6764, which would round up to a 5 because the next digit is a 9. So that would be grams of copper. And the last little corner up here, the whole goal of this experiment was to find the percent of copper by mass. So we have 0.67649 grams of copper over 0.97 grams of brass. Then we'll just simply multiply by 100. And because, again, we were limited by our 2 decimal place balance, we're just going to have to go with 2 sig figs in our final answer. I'll just chuck in an extra 1 sig fig just as a little subscript there, but it would be 69.7% copper, and that's by mass, so M over M.